Let's get started. Hi, everyone. Welcome to lecture 10. Today we'll talk about training neural networks. So this is a part 2 of the lecture. So we saw part 1 on Tuesday. So before we get into the technical stuff, so project 2 is due on Tuesday. The autograder is up. I sent an announcement on Tuesday saying that it's up, and I've seen like few submissions, successful submissions. So I think it's good to go. Please do submit early on. I've given like 5 attempts per day. So even if you are like partly finishing up the projects, have this habit of submitting it so that you know what to expect. Yeah, so it's due on Tuesday. I hope everyone has started working on it. Okay, some notes on the final project. So I showed this list of tasks that is relevant to the final project. Today I want to highlight the second part, which is the in-class topic or paper presentation. This will be done in teams. So for this, I think the most critical thing is to form the team. I know most of you have already have your team on the spreadsheet, but I think it's still like there are few people who have to update. Maybe you guys already formed the team, you have just not updated on the spreadsheet. So please go ahead and do that. Please try to do this by Sunday. I'm not like making it as a hard deadline as such, but on Monday, I would like to release an announcement saying, okay, these are the groups, these are the topics of interest, so that we can think about like scheduling their presentations for the second half of the course. So in-class presentation from students will start on 2nd of March. So yeah, if you haven't updated the sheet, please do so. That's the whole point here. And one other thing that will happen before your in-class presentation is to have a meeting with me the previous week, so we can work on the draft of the slides to see what content to be included and how to do the presentation. How do you like split stuff across your team members and so forth. So more announcements on that will come soon. Okay, so to recap what we discussed in the last lecture, we talked about activation functions, data processing, data pre-processing, weight initialization. We got to a point where we said we'll discuss about regularization in this lecture, and we'll also talk about training dynamics. And I'll give a hint of what we can do after training, but I'll not go into the details on that. Okay, so we talked about activation functions, and I think the gist of it is there are many variants of ReLU, but it's always good to start with ReLU before you try to look into other variants of it. And mostly these variants are going to bump up your performance by a small number. So it's always good to start with ReLU. We talked about data pre-processing and how this looks like batch normalization, but here we are focusing more on the raw input data than looking at the data from the previous layer. That's the key difference. And we also discussed about weight initialization and how to kind of get a sense of what is a good initialization in terms of weight. And after that, we were like, okay, now everything is set up. Let's say the model is training. What do we do here? What if it actually overfits? What are the things that we should be making sure we are doing here? So if this is a scenario, I know we have discussed this quite a bit already. If the training accuracy is pretty good, whereas your validation accuracy is not as good, the guess is that it's overfitting. So we have to add noise or some sort of regularization to your loss. So going back to the previous lectures, we saw this a loss to be a summation of 2 terms. One is the data loss, the other one is the regularization term. And you can have variants of regularization like L2 regularization, L1, and so forth. And commonly used is L2. And I think we also had a quiz on that on that aspect. One other regularization that you'll commonly see in the modern neural network architectures is this technique called dropout. So essentially what you're trying to do is you're trying to set some of these neurons to be zero, meaning you're trying to remove them from the architecture. You're kind of dropping them off. And commonly this is done with some hyperparameter, let's say with 50% probability. It's almost like every neuron, like you draw a coin and flip and say whether it's going to be there in the training phase or not. So here is an example with a 3-layer fully connected neural network. So if you look at it from the implementation point of view, especially here, right? So this is basically your linear expression followed by ReLU. And then this is where you're creating a mask for dropping out some of these neurons. And you're dropping it here with this step. And now some of these outputs are not considered for the next layer. So this is the simple thing that you can do to add randomness in your training phase. One other way to look at what is dropout actually doing is to see that if you imagine like each of these neurons capturing some sort of representation, during the training process, this is going to randomly drop off the neurons, right? So you are trying to capture redundant representation. At the same time, you want to make sure that you are not trying to fit for all the representations to do your task. Even for a subset of representation, your network should be able to have good performance. So for instance, here, let's say you have like 5 neurons that talks about the classification of whether it's a spot robot or not. Let's say each of them are like capturing different representations. Say one is capturing about like the fact that the robot has 4 legs. The color is yellow, has 1 arm, joints, and let's say the body is cuboid. But even if it sees a subset of this, it should have a good guess that it's a spot robot. So that's the whole point. And we don't want it to be while we want to have the expressivity by capturing all the information. We don't want to make sure that all the neurons are necessary for doing this classification task. Is that clear? Yeah. The another interpretation here is that during the training process, imagine you have like lot of epochs or a lot of steps that you're taking, and in each of the training step you are dropping off neurons. So if you think about it, it's actually an ensemble of a large number of models. Like each step would have its own unique network with certain neurons being dropped off, right? So yeah, so this is another interpretation where you can think that in the training phase, you have ensemble of neural networks and they share parameters with each other. So we saw what is being done during the training. And now let's think about what we should be doing on testing once you have a dropout in your training. So in the dropout, especially in the test time, what you're actually doing is it might have different output every time because you are randomly having a mask. And we don't want that during the test time. Training time, it's fine. But in the test time, we don't want that feature to be there. So we want to kind of marginalize out this randomness that you're introducing with this masking. And one way to do that is to think about this with the concept of expectation. However, doing that mathematically is hard. So we'll have an approximation of doing that. For instance, imagine this one single neuron, which has 2 inputs, X and Y, with weights W1 and W2. During the test time, we wanted to have this expectation of W1X plus W2Y, right? But during the training time, because of the dropout, it basically is a combination of these variants, where W1 and W could have values of 0 or 1. So these are the 4 different combinations that you'll have during the training. And the easiest way to think about it is if you average out all of these different expected values, you will see that there is a scalar that is being multiplied in the training phase. So all you have to do in the testing phase is to use that scalar value, which is also called dropout probability. So imagine during the prediction time, you have H1, H2. You just multiply with the P, which was the dropout probability that you had during the training phase. So in summation, if you look at the training module or training function and prediction function, in the training function, you have the dropouts that we saw earlier. In the testing or during the prediction, you actually have that scalar being multiplied. This is an approximation in which you are avoiding the randomness during the inference time or during the test time. Yeah? Okay. You could also do this using what is known as inverted dropout, where you divide by the same scalar during the training and have your prediction function like you had before, simple enough, like not having the scalar being multiplied. Again, this is just a variant, and both of them are the same thing. Okay, so so dropouts you will actually see mostly in fully connected layers, and especially with the fact that fully connected layers are the ones that takes a lot of parameters. And if you are dropping out, it's essentially is good in terms of computation. And one other thing to note is most recent architectures like GoogleNet and ResNet, because they do global average pooling, you would probably not see dropout in such architectures or implementation of such architectures. Okay, so dropout is one way of doing regularization, right? And if you want to generalize or summarize what regularization is actually doing, you're adding some kind of randomness so you don't overfit to your training data. And during that testing time, you have to make sure that you are averaging out that randomness. You don't want to have prediction being very random. You want to have that to be consistent. Yeah. And one example that we saw in previous lectures was this batch normalization, where we normalized over the mini batches that we were using. And during the testing, we used the running average that we calculated during the training phase for during the testing time, right? If you remember, that's what we did. So you'll see in ResNet and later architectures, L2 regularization and batch normalizations are like commonly used. So if you're thinking about regularization, you should definitely remember L2 and batch norm. Dropout is a specific technique, and you'll often see in network architectures, but that is something. One other way of inducing randomness during the training is by doing data augmentation. So you load an image and it's labeled, and you pass the image through the CNN, and CNN gives you a score, and then you can compute a loss with respect to the label that you have for that particular data. So a simple way of doing data augmentation or adding noise externally is to have an augmentation that says, okay, let me just like do some operation on the input image, transform the image to something else, and that gives you additional data, which means you are adding randomness to some extent from the data point of view. Here it is basically inverted, and also like there is a saturation and exposure being changed. So we'll see some common techniques in data augmentation. So data augmentation is like very common and like very highly recommended to be done, because in addition to regularization, it also adds more data. So you have more samples, more variations, and especially if you know your application, you can add invariance to your neural network by augmenting your data. Yeah, right. So it's a common practice to have data augmentation for your training data. And obviously it increases data as well. So that's good to have. Okay. One common thing that you would see is like this horizontal flips, where you're basically flipping the image. And again, there are like many of them. So I'll try to like go through each of them, but I'll do it very briefly. So one would be random crops and scales. So in the training, especially this is something that ResNet has done, where you would pick a particular length, and then you would like create an image with that particular length as the size, and then you will randomly crop an image. And basically, it's basically scaling and cropping your input image. And you would want to do the same thing during the validation so that you are averaging out the randomness. For instance, here, you will resize the input image into 5 different scales. And then for each size, you use like 10 crops and average out the performance. So that's how you'll calculate your validation error. So one other thing that you could do is you can randomize contrast and brightness. And you can also do much more complex thing than that. Like you could do like principal component analysis on each of the channels and do a particular offset in that particular direction of the principal components. This is seen in AlexNet and ResNet. You can also do a combination of transformations. For instance, let's say you have a repository of transformations like geometric transformations like rotate, translate, shear, but you also have color transformations like sharpening, contrast, brighten, and so forth. You could do that sequentially. So one example would be that, okay, there is an original image, you are doing a shear transformation followed by a contrast. You can also randomize the magnitude in which you do this sequentially. But the thing to remember is every time you try to figure out this randomly during the training, you're adding hyperparameters, something that you'll have to figure out for doing the training. So, especially in the research that kind of talks about data augmentation, you'll see a lot of creativity in terms of how they do this augmentation. Of course, we haven't covered all of them. We've covered like the basic set of augmentation techniques. And like I said earlier, it encodes invariance to your model. And one other thing to think about is like, what is the change in the image that should not like affect your output performance or the model performance. And you should also think about the tasks. For instance, if let's say doing the horizontal flip is probably fine, but doing vertical flip could be task dependent, right? Like you wouldn't see, let's say, a robot inverted, like standing on, like hanging from the roof. But that might not be the case for a water bottle. You might see the water bottle in various orientations. So depending on the domain and the task, you want to like get creative about your data augmentation. Yeah. Okay. Again, data augmentation is also one way to do regularization. So we talked about dropout and then data augmentation. So now let's look at some examples of regularization. Like I said, the principle here is you add some randomness to your training, but then during the testing or the validation, you marginalize that randomness with some techniques. So we saw dropout, batch normalization, data augmentation. There is also something called drop connect, which is different from dropout. In dropout, you're dropping the neurons, whereas in drop connect, you're dropping the weights. So that's the difference here. And this is not often used as dropout, but something to have in mind if your particular network requires that feature during the training. And one other interesting way of doing regularization is to have what is called fractional max pooling. So instead of having one fixed size for your max pooling filter, so we saw 2x2 filters, 4x4 filters, and during the earlier lectures. But let's say you have some sort of pattern in doing the max pooling, and it's And it's not consistent across the entire spatial dimension. So to pick an example, let's say you have 2 by 2 here. Here it could be 2 by 1, and so forth. The only thing to remember here, and if you're interested in that aspect, you should go and look into the paper, is that you wanna, while you're randomizing this, you should still make sure that your output after the max pooling has a similar dimension. Right? It cannot be random, right? It has to follow through the network architecture. So that's something to pay attention to. The other form of regularization is stochastic depth, and this is very commonly used more recently, especially on the ResNet, residual blocks. So you're basically skipping the residual blocks randomly. If you think about it, if you're skipping the residual block, it doesn't do much of a difference because the input is again connected to the next residual block. You're just like reducing the depth. So that's why it's called stochastic depth. And this has been like, seems to be like very efficient, especially in more recent papers on how to train a visual transformer networks. So if you're interested, you should look into this one. The other technique is to cut out, or what is called random erasing. So you basically replace a set of regions in your input with either a constant value or some randomness. So again, we are trying to induce randomness during the training, and this is one of the techniques to do that. The next one is you can actually blend different labels together. For instance, let's say we are having two images. One is on the pretzel, the other one is on the robot. You can blend them. At the same time, you can blend the output scores as well. The output score here is at 60% pretzel and 40% robot. Can somebody think about like why this is useful, especially maybe in robot perception? Yes. Exactly. So if you see a mirror or shiny surface and you're seeing reflection of other stuff in there, this technique can actually introduce that kind of randomness in your training and maybe be robust to those situations. So there is a particular way to sample like how much blending you're doing. It's using the blend probability, and we are trying to almost make sure it's either like close to 0 or close to 1. And of course, like if you're doing blending, you might as well like paste the scaled version of one image onto the other. Again, these are all techniques to improve regularization. It could work for certain applications. The other way to do is not on the input, but on the output, like doing the smoothing on the labeling side, saying that, okay, this is not 100% pretzel, maybe it is 90%, and add the additional signal to other variables in your other labels in your data set. So while I said like there are many of these techniques out there, you should always look into L2 and bash norm. I think that's the standard set of tools to do regularization. With Dropout, you will see them mostly on the fully connected layers. Data augmentation is always a good idea irrespective of regularization. And bash norm is probably not often seen in VITs or transformer networks. It's probably only limited to CNNs. Yeah, and any other augmentation or regularization techniques that you see here on the slide is basically can only improve your performance by a little bit. And it could significantly be dependent on the domain that you're looking into. Okay, so that kind of ends the first section on activation functions, data preprocessing, weight initialization, and regularization. So today we'll get into the training dynamics. Any questions so far? Yes.
Is there a way to classify glass as well, add glass also as a?
That's a very interesting question. I am not aware of any data sets that specifically does that. especially from a visual classification point of view. I know people have used sensor modeling techniques to figure out if a laser is hitting a mirror or a transparent surface, but not on the visual side, especially mirror and stuff. No. I mean, I do not know. Maybe there is, but I'm not aware of it. Okay, so let's talk about learning rate schedules and what you should be observing when you're training your neural networks. So we saw that most of the optimization routines has this learning rate as a hyperparameter. So these are some of the patterns that you will probably end up seeing when you're training your neural network. So on the x-axis, you have the epochs or the number of training iterations. On the y-axis is the loss function. So as you can clearly say, the yellow one, which is very high learning rate, you probably don't want that. What about the other three, like low learning rate, high learning rate, and somewhere in between? Any thoughts on what you would prefer?
High learning rate will make it learn faster, so it goes down quicker.
Okay.
Reach it close to that basic minimum, it will start the costly and the error.
So you need a combination of all of them to some extent, right? So you want to like come down really quickly, but then also do a very good search at the end, so you can actually go down and not saturate. So that is where the learning rate comes into picture, and the how you are updating the learning rate and when you are updating the learning rate. So one way to do that is to have a schedule that says, I'm going to reduce the learning rate after a set of epochs. Let's say at 30, 60, and 90, I'm going to like multiply the learning rate by 0.1. So if you do that, this is the pattern that you will generally see for the loss with respect to the training time. You can also do something that is more smoother than that. So using a cosine function. So here you have an initial learning rate, which is alpha 0, but then you update it with the cosine function. So you'll see a trend in getting the training loss more smoother than what you saw earlier. And while we are doing this in all this way, I think another simple way to do this is linearly. Like for every new training iteration, you're going to reduce the value of the learning rate in a linear fashion. And you can also use inverse square root. And maybe you should start with a constant. So I think that's where you should start training your neural, and then figure out like what is your learning rate update, and also when you want to do it and how you want to do it. Okay, so let's say we figured out our learning rate, and the loss versus iteration looks like that. But now you're looking at the accuracy over the iteration. So it's good to plot two things. One is your training accuracy and the validation accuracy. Especially here, one thing to note is you'll see that if the validation accuracy is sometimes going down or decreases, you want to have some technique or tool to actually capture when it was performing really well. It's always good to actually store your model or like have a snapshot of your model over the training phase, so you keep the best performing model on your validation data. So that's a trick to have. And you can also stop your training, so you can save on the computing, or at least you will know that, okay, this is not training good anymore. Maybe you should play around with the hyperparameters to make it better. So this is termed as early stopping, especially if you're working with engineers who are training neural networks. This is commonly used term. And you also want to make sure that you are storing the snapshot of your model whenever your validation is performing very well. Yes.
So does it matter if you use validation accuracy or loss for early stopping? Would you only want to use accuracy rather than the loss? I know they're related, but I don't know if one's better than the other.
So loss can depend on like many other things, right? It can depend on your regularization term and other stuff. But at the end of the day, you care about accuracy. So loss gives you a sense of whether your training is actually going well. Whereas the accuracy tells you whether you are getting the performance that you're expecting out of the network. So it could be that the training is actually going really well, but you're when you're looking at the accuracy, you have other I want to say perspective over the loss over the process. But again, like you can imagine, like if you can also plot the same thing, validation loss, you can also use that curve, but it depends on the loss function that you coined.
Often enough, like the validation loss would actually increase, but your accuracy would just keep getting better because it's not at that tipping point where like it starts predicting the correct ones elsewise, but it's still like starts predicting more and more correct ones. So
yeah, it's good to plot both of these, like to have a sense of what's happening. But at the end of the day, I think we care about the accuracy. Okay, so let's talk about choosing hyperparameters. One way to do that would be like to have a grid search. So you fix a number of values for, let's say, your weight decay, learning rate, and other hyperparameters. And then you do a grid search by selecting a combination of them and then running your model. This is grid search, but you can also do random search where you actually give a window within which those values can change. And there is a study that basically says random search is better than the grid layout because you have more expressivity in terms of where you're getting better performance, and then you can do a local improvement in those areas. If you're interested, I think there's a good paper on this from 2012. And one other characteristic to note is local values around the values that you chose. A small change in those will not have a huge impact on your performance. So in this particular slide, what you're seeing is you're seeing weight decay and learning rate. These are two different hyperparameters on the X and Y axis. And every sample that you see is a trained model or a trained instance. And the colors depict the performance. So you can see that there are bands in each of these plots. And you have a vanilla network, ResNet, and DARTs, like three different network architectures. But they have similar characteristics, right? Like anywhere in the local area, you're not having too much of a change in the performance. So when you're doing the search, you want to have like a bigger interval to figure out whether that particular area or the region is what you care about. Okay, so all of this sounds great. So many hyperparameters. What if you don't have too much GPU power to do all the search? Like, because basically when we are searching, we are running training on each of the selected search instances. So I think there are some common guidelines that people tend to use. So I'm gonna just use that to maybe tell you how to choose hyperparameters for your projects. So first thing is to do sanity check. So for every input, for a different input, you should have a different output, right? And then your gradient should not be 0. Your forward pass and backward pass should work, essentially. Should not have any bug in that. So that is probably the first thing that you want to check, along with what is the loss value that you're producing. The second thing would be to overfit to a small sample. So if you have a data set, curate mini batches of them and make sure you get 100% training accuracy for that particular small batch. In this particular scenario, you can fiddle around with your architecture, learning rate, weight initiation, whatever. But for this small batch of data, you want to make sure that you get 100% accuracy, especially on the training. Some things to think about is if your loss is not going down, increase your learning rate. if your loss is like exploding, then reduce it. The next one would be like, okay, now we kind of have a network that performs 100% on a small data. So increase the data, make sure you use all the training data. But also like make sure that you find what is your decay or the weight decay or the learning rate. And make sure you have a values in which you do the search. So a common way of doing this is like use these 4 values. This is what you'll commonly see being used, and do it for a small number of iterations. And now once you figure out your learning rates, you want to try to figure out like for few models, like what is the set of hyperparameters. So earlier we did only for the learning rate. Here we are doing for the set of hyperparameters, but you do it for a small set of epochs. So that's the difference between step 4 and step 5. And you refine the grid, like you are again like trying to refine your grid search, but you are trying to also train longer than what you did earlier on. And of course, like during all of this, you should be looking at your learning curves, especially by plotting what is a scatter plot, because your loss with respect to iterations can be very jumpy. So you want to have some sort of averaging that tells you the trend of your loss. You wanna look at both the mean and also the variance of the loss. Your variance should decrease, meaning they should not be too jumpy at later iteration, and the loss should also like gradually come down. So there are some characteristics in which that you might find useful. One is, let's say you have a loss versus epochs like this. So what this basically says is there's a bad initialization. So that's why it's not like jumping off from that location during the optimization routine. The other common thing that you'll see is plateauing or saturating, which means that you want to have like larger learning rate in that particular instance. And this is more like peculiar or like very specific instance. Let's say you have this particular plot where your loss was still going fine, but then you did a drop because of the step that you chose. This basically indicates that you did that too early. So you want to probably do it at a later iteration and not in that particular iteration. It was already going down, but you tried to step it out, and then it started being saturating from there. Okay, so in terms of accuracy and the epochs, this is actually a good trend to have. Your validation accuracy is increasing along with your training accuracy. They do have a gap, but there is an increasing trend for your validation accuracy. So which means you keep doing this for a longer number of epochs. As we saw earlier, if this is happening, this could be indicating that your training is basically overfitting, and which means you probably need more data and also increase your regularization. So whenever there is a huge gap, or if the gap between your training accuracy and validation accuracy is increasing, you probably want to think about adding more data or data augmentation or regularization. Yeah. This you might find, but the thing is the accuracy will be like very low. So which means both the training and the validation accuracy is almost close enough, but the value of the accuracy is not going to be like around 90 or something. It's going to be like very, very low, which means your network is probably underfitting. So in this case, you want to think about like having a bigger model so that it's more expressive in capturing representations. Or maybe you can also think about like trying to play around with higher learning rate. Okay, so in terms of strategy, you again go back to the 5th step and do this again and again until you're satisfied with your performance. So these are like simple guidelines to think about how to train your neural network. Any questions so far? Yes.
I guess in terms of, I think the plateau slide, so how would you know the difference between a plateau and approaching a minimum?
This one?
Yeah.
So you will see that it's not decreasing, right? It's actually staying almost constant. So that's the saturation or plateauing.
Could you have the same effect if you like hit a minimum?
Yeah, for instance, if this is not on this level, let's say if it is around here,
Yeah.
then we're good.
Okay. You just have to find out what that is.
Right.
Yeah.
Okay. Yeah, so again, there's a lot of things to play with, right? You have your network architecture, which we saw in the previous lectures, like which architecture do you want to use? And on top of it, like what is the learning rate? Its decay schedule and how are you updating it? Like, which means like what is the update and when are you doing it? And what is the kind of regularization you're opting for? I would say it's better to start with a particular network and their regime and go from there than starting from like scratch by yourself. And there are tools to look into as well. For instance, if you're using TensorBoard, TensorBoard has this way of like plotting all of these values. So you can look at the trends. You can also look at it from layer by layer. You can see what is happening to your gradients. So there's a lot of inspection that you can do with TensorBoard. It is also useful for plotting your results real time. So you can see images and their classes and results as well. So there are tools to do that. I think one other well-known is WNB, which is commonly used these days in industry. So if you're interested and if you want to like know about these tools, you should look into their tutorials. I think there are a lot of videos out there to do that nowadays. Okay. So one other commonly used value that people tend to track to see if something is wrong with their training is to track the weight update with the weight magnitude ratio. So apparently there is a sweet spot for the value. And if it is too bigger, too smaller than this, then you probably want to like look into your hyperparameters and see what's going on. Okay, I think that ends the discussion on training dynamics. I will not go into the third section, but I will leave the slides for you guys to discuss. I think somebody posted on EdSTEM about an ensemble kind of structure where I think was it you, Nikhil? Like you can have an ensemble of pigeons to kind of classify if an X-ray has a cancer. So, and which outperforms human performance. So it is very interesting to see ensemble networks being used in different ways. And you will also probably hear this in self-driving robot perception tasks, where they use ensemble networks to do segmentation and detection. So which is commonly used as well. Okay, I'm gonna leave the slides in here. You guys want to like look into it. I think in the next lecture, we'll talk about deep learning software. So yeah, I'm ending the lecture earlier today. I'm happy to answer any questions.